Good morning everyone. In this video we will going to discuss about asymmetric key cryptography. So the main mathematical concept which is required for asymmetric key cryptography is prime numbers. Actually prime numbers plays a major role in cryptography. That is especially for developing the asymmetric key algorithms. So why we need prime numbers, or why prime numbers are very useful in cryptography? First thing is about the uniqueness. So prime numbers will have the property that they can only be divided by 1 and also by themselves, making them building blocks of number theory. And also this has three critical aspects in the blockchain design principle. That is, it's based on the number of rounds, design function and key scheduling. So apart from this, the factorization is very hard. That is, the security of the cryptographic algorithm often hinges on the difficulty of factoring large prime numbers which are generated. And next is the modular arithmetic properties. Prime numbers will simplify the certain mathematical operations such as the group theory, where the order of elements in prime module field is well behaved and predictable. Prime numbers remains a cornerstone of modern cryptography technique, providing the foundation of secure communication, encryption and digital identity verification. So here the primality testing will play a major role. So primality testing is the process of determining whether a given number is prime or not. So here we are using Miller-Robin algorithm and Fermat's primality testing in order to identify whether the given number is a prime number or not. So a prime number is a natural number which is greater than 1 that has no positive divisors other than 1 and that self or itself. So primality testing plays a crucial role in cryptography, particularly in the development of algorithms like RSA, where we need large prime numbers. So there are many type of primality testing. As I said, we are using Fermat's little theorem. So the Fermat's little theorem is a power n minus 1 is congruent to 1 mod n. So when that theorem is proved, so n is a taken prime number. For example, if the n value is 2 means the a value can be between 1 and n minus 1. So when a power n minus 1 is congruent to 1 mod n is proved, we can tell that the given n is a prime number. So the major classification of primality testing lies in the deterministic prime testing, where we use a trial division method, and we also use Agarwal-Skiles scheme for testing whether a given number is the prime number or not. Also, prime number plays a major role in elliptic curve primality proving, which we call it as ECPP. This is a modern and efficient deterministic method which is based on elliptic curves. So elliptic curve primality proving, which is often used in practice for very large numbers, and they work faster than other deterministic method, and also this has first time case complexity. So next method is the probabilistic primality testing, which is, I said, Fermat's primality testing. So the formula is a power n minus 1 is congruent to 1 mod n, which holds 2. However, this test can falsely identify some composite number as a prime number. We call such type of numbers, or we call such numbers as Carmichael numbers. That means Carmichael numbers are the numbers which are proved as prime, making it unbelievable as its own. And next is Miller-Robin primality testing. This is a widely used probability testing. So this is more reliable than Fermat's test because it not only checks Fermat condition but also examines an additional property of prime numbers. If a number of passes of test several times with different random bases, it is considered as probably a prime number. So the error rate decreases when compared to Fermat's little theorem. So these are the two main theorems which are used for determining whether a given number is a prime number or not. So here also we have taken an example of a number which is a prime. So in order to determine this number is a prime number or not, we can use either a Fermat's little theorem or we can go for Miller-Robin theorem in order to find out this 1000024 prime number is a prime number. And also we had given another example. Just try it with this example 127 using Fermat's little theorem and tell me whether the 127 is a prime number or not. So and also you know about the factorization of the composite numbers. So when we go for factorization, or the normal way of finding the factorization of a given composite number is taking a GCD. So when we will tell the two numbers are co-prime means when the GCD of the two number is 1 means we can tell that the that is GCD of a comma b is 1, we can tell that a and b are co-primes, provided that a and b should be a prime numbers. So this is the way we are finding out the prime factors of a given number. And also there is another method for finding the GCD, as we all learned in the second unit, that is the one of the way to find the GCD of a given number is by using an Euclidean algorithm. So you all know that is this is the formula for using the Euclidean algorithm. And so just find out the GCD, and if the GCD of two prime number, or if the GCD of two number is 1, we can tell that the both numbers are co-prime to each other. So this is how, so that is what the prime numbers plays a major role in asymmetric key algorithm. So for testing the prime numbers, we are using Fermat's little theorem and Miller-Robin theorem. So we will see the problems based on these two theorems on the next sessions. Thank you.